Hey everybody, it's Jeff for CS161B. We're getting close to wrapping up the class here. We're in the final two modules here. With Module 9, which we're going to cover here in this video, we're going to spend some time talking about pointers. And I have some slides as well here that kind of describe what we're doing here to some extent. Pointers is the topic that gets you going from what I would call the beginner to intermediate developer into the more advanced programmer. And um, it's not intuitive, and it may take some time to understand the concepts here with pointers. And in this module, we're just going to really skim the surface of pointers. We could spend 3-4 weeks on this, and in the advanced classes, that you'll be continuing to take, you'll get more and more exposure to these as we go forward here. And so before we jump into some specifics, let's set some context with some information that you probably already know. And if you don't, well, you certainly know it to some extent, right? And so it'll be a refresher as well as an assistance here. If I take some memory here, and every location in memory can be accessed with a unique address, and that's what this column here is on the left. Okay, if we look at these address values here, they're 8 hex characters, right? So that's a 32-bit address, because each hex character represents 4 binary positions. You should remember this from CS160, right? And so, for example, 1000 ABC2 in binary is going to be 0001 for that first digit, 0000, 0000, 0000, and then A is 1010, B is 1011, C is 1100, and 2 is 0011. That would be your binary equivalent of this address. And so if we have a 32-bit int being declared here and a 32-bit int being declared here, and maybe we have a double declared here, a double is 64 bits, so it takes up 2 spaces in memory like this. And remember that a char is only 8 bits. And so we can actually hold 4 of them in a single 32-bit spot, and that's why I have a 4-character array that's at this address. Okay, so today in programming, you never need to know what the addresses are of where data is. You may care relatively where things are to each other, but you never care what that absolute value of that address used to be. That hasn't been true for a very, very long time. And so, in fact, when you run programs over and over, they will be, that data, the program and that data will be in different addresses. It gets abstracted by the operating system. And in CS201, you'll get some introduction to that. Okay, but there are times where we want to access things by the address, even though we don't care what the value of the address is. Okay, and so if we create a variable and we have this variable int b is equal to 42, then there's a location in memory. We have no clue where in memory that is, but that location in memory is associated with the variable b. And whenever we access b, we're going to get the value that's in that location in memory, which in this case is 42, and of course we can change that. Okay, if we want to introduce the concept of a pointer, is what if we want to know what that value is? Okay, and we do that by using the ampersand as a prefix to the variable name. Okay, so we're going to demonstrate this here. I wanted to kind of walk through what it looked like first, and now we'll go ahead and demonstrate it. The code should run equally the same on the Linux server and Replit. I'll probably stick to Replit most of this demonstration, but we'll see, right? So if I create my integer variable, I'm calling it x here. I guess it was b in the slides, but it doesn't really matter. right? And I am going to declare, I'm going to do two things here. This we're very familiar with. Okay, this less so. Okay, so let's see what this does here. Ugh. Let's run this and see what this does. Okay, so x is an integer variable with a value of 42. When I declare this, the star indicates a pointer. And a pointer is always has a value of a location of an address. And the ampersand always means the address. And so I'm saying that I'm taking the address of the memory that contains 42, which is just another way to describe x. And I'm going to set that value equal to a pointer variable called xp. Okay, and so these are just different ways of representing the same location in memory. Now, if I print the pointer itself out, let's see what we get. I get a big long hex digit. Okay, this is the address, right? And we can confirm that by doing this. And you can see they're the same. Now, I could even just remove all this. And so, because I don't need to declare a pointer to have access to the address. So in fact, it makes more sense to kind of do this in an opposite order. So now I might declare the pointer to point to the address. And then if I print out the value, I print out what this means is print out the value that XP's address is pointing to. That's what star XP means. Okay, so star is a pointer. It's an indirection operator. And so when I say star of something, it means find that location and tell me what's in that location. This is called indirection. Okay? And so now I also could do this. And so you can see you have your hex address and you have your base 10 address. If you prefer, I would say that 99% of the time, addresses are better in hex. They're just, once you get used to the hex notation, right? But you can convert it to a long, which is a 64-bit integer if you want. Okay. Now we can change the value as normal, right? We can say as x is equal to 24, and we can we'll print that out, right? We can say x is equal to 36 or 38, and we can say the pointer xp, I want to print the value of that. And you see I'll get my 38 there. One thing that I haven't shown you how to was what if we just print xp by itself without the star? What does that do? Because that's an address, right? So in other words, if you print a pointer variable without its asterisk, it's the same as printing the address of the variable you're trying to access. And I think one reason that pointers can be confusing is because if you look at example code out there on the internet, you'll see uses where the star is being referenced, where the ampersand is being referenced, where there's a mix, and it can be confusing here. Okay, and so the last piece of this that I'll show you right now here is instead of changing the variable directly, I could do this instead. I can say, hey, I have a pointer. I want to change the value in the location represented by that pointer. And when I do that, you'll see I get my 12 here at the end. So I'm kind of showing you all the different ways you can change the variable's value here. I could venture with many of you that you'll watch this several times and it will be very fuzzy. You might watch it many times and it'll be fuzzy. This does take a little bit of time here, okay? And it's only with practice and kind of seeing the examples over and over will it start to really gel and make sense. Okay, again, if we jump back to the PowerPoint here, right? Well, I guess I did use X. So X. So here, let's add something to this slide here, right? So if I do this, this is gonna, X is a variable. So when I print out the value of the variable, I'll get that 42, right? If I print out the address of X, I'll get whatever this value is. And if I assign that address to a pointer variable, then I can access the contents through that indirection operator. Okay? And so that's kind of what I'm showing you here. I'm going to do it one more time. Okay? Because I think the repetition is helpful here. So int x equals 42. Okay, we know what will happen here. I can change the value. And we know what will happen here. If I print out the address of X, and I should have kept it from the previous run, you can see the address is different each time I run the program, right? Because like I said a few minutes ago, when you run a program inside, say, a Windows operating system or a Linux operating system, the memory used by the program isn't always the same exact memory every time. And so this address will change. Okay? I could say so what I did here was I basically said, I'm going to take the address and I'm going to use the indirection operator and say, whatever this address points to, I want to access the value that's inside the address. Okay, the alternate way to do that would be to create a pointer value and set it equal to that address. And then I can print it out again. Lots of different ways to do it. Okay, the most common way to do it is like this. I should get 24 and 24 here, right? X is an integer variable. P is a pointer variable. I think in the previous example, I used XP to indicate a pointer to X, but they don't have to be, right? This could be whatever name you want and whatever name you want. Okay? So again, the indirection operator is the address or reference operator. And we've seen that the reference operator before when we're doing functions and we're passing by reference, right? So same kind of thing is what's happening there, right? Okay, so that's the Blitz introduction of what a pointer is. Okay, arrays are a little different. Okay, arrays can be both a little tricky, but also in some ways more intuitive here, right? So if we create a character array, we know what that's going to do, right? That's going to print out a capital B, right? Okay. If we do that, we also know what that's going to do. That's going to print the whole array out. Okay. And if we do this, we are going to get the address of where that first character in the array is. And you can see it's just a random address. We don't know what that is here. Okay. And then of course, we'll do pointer arithmetic here in a moment. We'll come back to that. Okay, let me show you another example. Let's do it with integers. Okay, so we're going to create a 3-element array, and we're going to do the same thing here. Okay, we know what that's going to do, right? That's going to print out 21. Okay, what if we do that? Not sure we've ever done that before. Okay, we have an integer array, and we're just printing the array. Now, if this was Python, it would print like the whole contents of the array or something like that. What this does is it prints out the address of the array here. And boy, at first I thought it was the same. Look at that. That's a coincidence there. Look at that. There's only one character difference here between these two locations here. And so printing out B is the same as, I think it is, let's see, is the same, right? Because the first location, the address of B0 just happens to be the same as B here with an integer array. Now we can do this, and you're going to see we're going to get successive numbers here, right? We're going to get C98, C9C, and CA0. And we're going to come back to the sequence of this here in a moment. No, actually, let's do it now. Actually, let's talk about pointer arithmetic now. I'm going to run it one more time. Yeah, that's good. Okay, so if we look at these three values, all the digits are the same except the last two digits. And I'm just going to put this here temporarily as comments. We're going from F8 to FC to 0, 0. And actually, let me do one more. Okay? And so if we look at this from a binary perspective, 6F8, if I add 4, 8 plus 4 is 12, right? Which is the hex value C. And so that is equal to 6FC. And if we add 4 to that, C plus 4, 12 plus 4 is 16. And so we actually, this would be 15, right? So we have to increment that by 1. And so that turns to 0. The F also overflows and turns to 0, and that turns to 7. So what you see here is that each location of this integer memory has got an address of 4 from each other. If I run it again, we should see the same thing. 8C and 0 again. Eight C and 0 again. I want to try to make the math a little simpler here. Oh. Got to force it to be used. Still doing the same thing. These guys are still the way they're being organized, but it's okay. I think hopefully it makes sense here. Again, 68 hex plus 4 is 6C, plus 4 is 70. Okay, and then sometimes you're seeing a wrap in that third digit, sometimes you're not. Okay, now, so it's showing that these addresses of these integers are 4 apart because because we're doing byte addressing here, right? And so every location holds just a byte, which is different than my PowerPoint example. So now let's try something else here. Okay, now that's confusing because I just subtracted the address of 2 from the address of 1, but I got 1. But I should have gotten 4, right, per the math I just did, right? And so that seems wrong, you might think, okay? But the point that I'm trying to make here, or I'm trying to demonstrate this here, is that when you do address arithmetic, it takes into account the data size. Okay, now let's change this to double, and now let's see what happens. Okay, now if we look at our addresses, we went from 9B0 to 9B8 because our double takes up 8 bytes of memory. And then 8B8 to C0 is 8 bytes of memory. But when we still do the math, it still is only 1. So this math here takes into account the data size. And what's really cool about this is I'm gonna add some more here. 1, 2, 3, 4, 5, 6, 7, 8. I am going to, let's do this. Okay, so we're going to print out the arrays. Now I'm going to say x is equal to 3, and if I want to move things around in the array by updating the pointer, here's what we would do. So I'm going to create a pointer, and I'm going to set that equal to the address of 2. And then I'm going to say p is equal to p plus 4. And then I'm going to say the value at that pointer is equal to 99. And then I'm going to reprint my list. Go back to ints. Okay, so what I did here is I set P to this address, to the address that contained the 43, but then I increased it by 4. Okay, and so I went 1, 2, 3, 4, and so therefore I modified position 6 with the 99. Okay, but again, if I print out the address of B2 and the address of B6, they're more than 4 apart. In fact, they're 16 apart. If you look at the number, 38 hex to 48 is a difference of 16 in base 16. Right? We can do this if it helps with your. Remember, if you were like puzzled by when I was doing that hex math in the previous example, we could put long casting around this, and you can see we went from 1288 to 1304. 1304 minus 1288 is 16. Okay, so this is how the address arithmetic works. We could go ahead and again, we can change this to double and do the same thing, and instead of them being 16 apart, they'll be 32 apart. Okay, so the more sophisticated programming is going to be where you are moving within data structures like arrays, counting on the fact that it does that address arithmetic for you automatically, which is kind of cool. All right, one of the things I wanted to show you next is in the textbook. So we've basically covered the first 3 sections of chapter 15, and we're going to talk about functions a little bit more. We've done this already. We've done this already, but what I want to show you is this example. Okay, and let's start by putting it into the code. Okay, so let's look at what the code is doing here. I have 2 variables, x and y. I'm passing them into my function along with a pointer, and I'm returning that value, which should be the minimum, right? If x is less than y, I set my min to the address of x, else I set my min to the address of y. And so instead of getting 5 here, I get some bizarre, random, illegal value here. And the question is why, right? I want to return a pointer to my value, but it's not letting me. In your textbook is this video right here. Professor Iyer walks through this in detail here. I think it's like an 8 or 9 minute video. I would recommend watching it. But what I'm going to do is I'm going to give you a quick tutorial of what that looks like, and I'm going to use this Python. Let's start over here. Yeah, this pythontutor.com, which you can do stuff in C++ as well. I don't think I've shown this in this class yet, actually, but this is a way that you could step through the code one statement at a time. Okay, so let's do that here. So right now we're at step 1. We're at line 6, where basically we've entered our main function. I click next, and we move down here. I click next 1 time and watch what happens here. Okay, so x is set to 5 and y is set to 10. Now I do it again. Min is a pointer that's pointing to null. I haven't mentioned this before, I don't think. Null is just a defined pointer value that means I don't point anywhere. And it's a good way to check to see if pointers are initialized. Okay, so I'm going to keep going. I'm going to jump into the function. Now you can see I have a new blue box. This is the variables x, y, and min that are in the function. The parameters have been passed. X is set to 5, y is set to 10, and the pointer to min is a null pointer here. So I jump to line 15. X is less than 5, so I jump to 17, and I set min to the address of 5, and that's what this arrow means. So min is a pointer value setting me to the address that the 5 is in. But when I click next again and return out of the function, I got to go one more here. I'm going to return min. I get the skull picture here, and I get a message here. The skull means a pointer points to memory that's unallocated or misaligned with data boundaries. Skull locations are approximately matched to the pointer's real address. Okay, so in other words, it's either unallocated. What happened here is that all of these variables existed only in the scope of the function. And when the function was finished, those values and those variables went away. And that's why this doesn't work here. Okay? If I run this on the Linux server, I found that it worked some of the time. And the point here is that you have to be super careful when you're sending pointers out of functions. And you want to make sure that they're not local values. Otherwise, you will be pointing to data that really technically no longer exists here. This is confusing. I had to run this a couple times to refresh myself exactly on what it was doing. And so again, I would recommend you watch this video. She does I was going to just redo the whole dang thing, but there's no reason to. It's right here in figure 15.4.5. Just watch the video. And she does a really good job explaining this problem, and it can be quite a subtle bug here. Okay, this is a very quick overview of pointers. This section is not that deep. Conceptually, it can be pretty challenging, like I just said. Like I said, it's an advanced topic, and we are leveling up here. So I'm giving you just an introduction here. Good next steps here. If we look at what the rest of the chapter is, it's going to be more examples doing stuff that you've really already done, right? Prompt a user for some sales and print the sum. You know how to write this stuff in your sleep by now. Now do it with pointers, right? And find the maximum. Now do it by pointers. Okay, and that's chapter 15. So short session here for us this month or this week here. There is an assignment. There's a Linux lab, of course, and then there's an assignment here. Just a reminder, if you haven't started thinking about your final project, you are starting to run out of time here. So take a look at that and send me any questions if you have it. Otherwise, go ahead and work the discussion in the lab and start to get used to pointers. It will be a journey. The objective is not to learn pointers in this class. It is to get an overview pretty much just in this 1 week, really. We will wrap up the course material in one more week with a session on debugging tips and tricks, which is kind of some fun stuff. And we're getting close to the end. So we'll talk soon.